Hey, Dr. Clark coming back at you with another Check Your Understanding video. We're in section 7.2. And this problem has an undamped spring mass setup, a mass of 1 kilogram. And so we're kind of seeing this setup here. Notice it's undamped, so we don't have any friction term. And they're going to have us do some modeling here. So if you think about, what is the model for the undamped spring mass? That's what you should be thinking. A force of 8 newtons stretches the spring 2 meters. A time-dependent external force of 16 e to the minus 2t newtons is applied beginning at time t equals 0 to the mass from rest at position 6 meters to the right of the equilibrium. Okay, so if we're thinking of this as sort of the x-axis here, maybe this is x equals 0 equilibrium. They're going to pull the mass over 6 meters to this position and then let it go from rest, and it will probably, oscillate back. That's sort of the idea. And they're asking us to model this scenario. So the first thing would be for part A, we would use the standard m x double prime plus kx equals f of t. That's the standard undamped model. They already told us the mass is 1 kilogram, so m is equal to 1. They have not told us what k is, but they do tell us that the force is 16e to the minus 2t. Now, the information they give us is that 8 newtons stretches the spring 2 meters. So kx equals 8, x would be 2 if an 8 Newton force stretches it 2 meters, that tells you that the spring constant is 4. So they're giving you the spring constant sort of contextually by telling you how strong this spring is. So that means our model is x double prime plus 4x equals 16 e to the minus 2t. That is the differential equation. Now a model should have initial conditions, and since it's a second order model, we should have 2 initial conditions, one for position, one for velocity. It said it was released from rest. That means the velocity is 0. 6 meters to the right, assuming that right is positive as pretty standard, x of 0 would be 6. So that's part A. That's the initial value problem that models the scenario. For part B, use the method of Laplace to solve the initial value problem. Okay, so we're going to Laplace transform this entire differential equation. Lx double prime plus 4x equals the Laplace transform of 16 e to the minus 2t. Now, in order to do this, and we're probably going to have to spill on to the next page, we're going to need some formulas for Laplace transform, and I have put those here. So one says if you Laplace transform the derivative, that's s times the Laplace transform of the function minus that function evaluated at 0. And then we've got Laplace transforms of, L of e to the at, L of sine of t, L of cosine of t. And we'll need those in order to solve the problem. So the first thing we here have is, I guess by linearity we could divide this into L x double prime plus 4 L of x, and that would equal 16 times L of e to the minus 2t. Well, a in that case would be negative 2, and so we'd have 1 over s minus negative 2, or 1 over s plus 2. So 1 over s plus 2 for right-hand side. And then we can apply s L of x prime minus x prime of 0 plus 4 L of x equals 16 times 1 over s plus 2. And we already know right from here that x prime of 0 is 0, so that term goes away. And then we can apply again this rule one more time. So we would have s, and then in parentheses, s L of x minus x of 0 this time, plus 4L of x equals 16, 1 over s plus 2. I'm going to copy that term and bring it down a little further so we can work with it. We were told that x of 0 was 6 earlier in the information. Whoops. So right here, x of 0 was 6. So this gives us s squared L of x minus 6s. Very easy to make a mistake here with this 6 times s. You want to get the 6s. It's probably the most common mistake on a problem like this. And that means, doing some algebra, s squared plus 4 times L of x is equal to 6s plus 16. Well, I'll just write that as 16 over s plus 2. I think that'll be easier. 16 over s plus 2. And that means that L of x is equal to 6s over s squared plus 4 plus 16 over s plus 2 s squared plus 4. All right. Okay. Now, what we would want to do is get x of t. And to do that, we would do the Laplace inverse of right-hand side, right? That's the goal. But in order to do that, we have to apply our partial fractions decomposition to this term right here. So sort of as an aside, let's figure out 16 over s plus 2 s squared plus 4. That should equal a over s plus 2 plus bs plus c over s squared plus 4. Because s squared plus 4 it does not factor. It's an irreducible quadratic, so we need the linear term in the numerator. This is a linear term, so we just need the constant in the numerator. And if we multiply by the denominator, we will get a times s squared plus 4. And then we will get plus s plus 2 times bs plus c. One thing I like to do that often is helpful is if I just set s equal to -2, then I'll get 16 equals a times -2 squared is 8. 4 plus 4 is 8. So I can figure out that a is equal to 2 from that. But because this term here I can't make it 0, we can't sort of play the same game, so we're going to have to probably work the other one out. But we know a is 2, so we have 2s squared plus 8. And then we're going to multiply this other one out. bs squared plus 2bs plus cs plus 2c. And this should actually get us there because here is 2s squareds and here is bs squareds, and there are no s squareds over here. So it has to be the case that b is equal to -2, just because the number of s squareds on the left has to match with the number of s squareds on the right. And then we could look at a 16 and an 8 and a 2c. Those are all the constant terms. So c would have to be 4 so that 8 plus 8 is equal to 0. Or sorry, 8 plus 8 is equal to 16. C should be 4. And then these s terms should work out. If we did -4s plus 4s, that's 0 s's. So the s, yeah, okay. So that leads us to a was 2, so 2 over s plus 2. And then b is -2 and c is 4. So -2s plus 4 over s squared plus 4. That can replace that term right there. So let's copy this. We'll paste it down here. And we will replace this 16 s plus 2 s squared plus 4 with this term right here because we just proved algebraically that it's equivalent to it using our partial fractions. And so now L of x after a certain amount of algebra is 2 over s plus 2 plus 4s plus 4 over s squared plus 4. We might as well combine these two terms together. Okay. And now we can find x of t. X of t is the inverse Laplace transform of 2 over s plus 2 plus 4 times s over s squared plus 4 plus 2 times 2 over s squared plus 4. Now, hopefully you can see this 4s is the same as this 4s. And the reason I factored the 4 out is because s over s squared plus 4 is on my list over here. Here's s over s squared plus 4, right? And k is equal to 2 in this case. So that should be a cosine of kt or a cosine of 2. So this should be cosine of 2t, but then times 4. Here we have 2 over s squared plus 4. And 2 times 2 is 4. So I have factored out the 2 because I want a 2 in the numerator because the sign has, I need 2 over s squared plus 4, right? That would match this form k over s squared plus k squared. Okay, so that is sine of kt. And the other one is e to the at, right? So if you apply those methods to the inverse Laplace transform, you're going to have 2 times e to the minus 2t plus 4 times cosine of 2t. Again, here, k is equal to 2, k is equal to 2, and a is equal to negative 2 in this sort of, in that naming system. And then this is 2 times the sine of 2t. And that is your final answer right there. And I did graph it previously. So let me bring the graph up here. You can see that I have exactly 2e to the negative 2t, 2 sine of 2t, and 4 cosine. That function satisfies f of 0 equals 6 and f prime of 0 equals 0, which you can see from the graph. It starts at 6 with a slope of 0. And if you draw that graph, that is what you get. This term is transient, and then these terms persist because it's an undamped harmonic oscillator. So hopefully you were able to get that answer right there, but that was a little bit of a long problem. So if you did, you should feel pretty good about your skills. We'll see you next time.